Hi, I'm Yuan Huai Tsai from National Taiwan University, and today I'm going to present my recent work, Subseasonal Forecast of the Northern Queensland Floods of February 2019, and Causes and Forecast Evaluation. And this work is also contributed by Professors Mengming Lu, Zhongxin Zui, and Dr. Yiming Zhuo. And this work has been published to MDPI Atmosphere. Okay. So, in late January and February 2019, Queensland was hit by a disastrous rainfall event, and the event caused 18,000 residents to lose power and hundreds of others to evacuate. And the floods led to huge losses for farmers and estimates of 625,000 head of cattle and 48,000 sheep were killed. So in this study, since this is a disastrous flood event associated with extreme rainfall, so we are going to examine two scientific questions. First, what large-scale factors are directly linked to this event? And how will the S2S prediction models predict this event at the extended range? So in this study, we are going to use several observational data sets. CMOR precipitation data with horizontal resolution of 0.25 degree, and NOAA's outgoing long-wave radiation data with resolution of 1 degree, and area intrawind wind field with resolution of 0.75 degree. And the data time range is from 1998 to 2019. And the four of the subseasonal to seasonal prediction models are applied in this study. POM model from Australia, CMA model from China, and the ECMWF model from Europe, and then NCEP from the USA. And this is the forecast lead time, resolution, sample size, initialization frequency, and the high cast information, and which is listed here. And not all the model provided forecast data in a daily basis. So in this study, we are going to analyze the 2018-19 Northern Queensland subseasonal peak rainfall event, or the SPRE. And the SPRE is defined as the accumulated rainfall amount as the highest among all successive 3 pentad accumulated rainfall within a time window from December to February 3 months. So in this figure shows the mean precipitation, 15-day accumulated precipitation, and the mean low-level wind field during the flood event, January 26 to February 19. And we can find that the box area over the Townsville and the marginal sea has the maximum precipitation. So we can plot the 15-day accumulated rainfall data running by pentad, and in this figure, and the gray shading area is the climatological range, and the blue curve is the time series in 2018-19. So we can find this is the SPRE over the northeast Queensland. And it also broke the 20-year record revealed in the CMOR precipitation. And if we take a look at the wind field, we can find that this event is associated with enhanced monsoon and monsoon depression over the northern Queensland. So the influences from the monsoon and monsoon depression can be quantified using the indices. So we plot the low-level zonal wind over the average over the black box, and plot the zonal wind shear between the two red shaded area. And we can find that during the flood period, or the SPRE period, the 15 day has a strong monsoon flow and the monsoon depression. So we can find that, and the monsoon depression and monsoon flow is the strongest among the entire season. So we can find that this is a slow-moving monsoon depression, and which is appear as the culprit for the disastrous rainfall event. And what are the climate drivers related to the enhanced monsoon depression? So here we plot the Hoffman diagram of precipitation in shading, and the solid contour is the Madden-Julian oscillation in convective phase, and the dash contour is the equatorial speed wave is in convective phase. So we can find that the SPRE is concurrent with the two types of the waves. So the SPRE is mainly induced by the anomalously strong monsoon depression, and the monsoon depression is modulated by the convective phases of the main MJO and equatorial Rossby wave. And the equatorial Rossby wave was originated near the dateline over the Central Pacific, and it is associated with the El Nino warm sea surface temperature that induced the deconvection over here. So next, we are going to evaluate the S2S prediction model's ability. So we are going to examine in two aspects. The first is the monsoon depression index variability. So here we evaluate the relative intensity of the low-level wind shear index during the current times of the SPRE, and this figure is the composite range of the monsoon depression index during the SPRE, and we can find that in the entire 45-day period, the 15-day SPRE has the strongest monsoon depression index in the climatological data, and we can collect the 15-day monsoon depression index and convert it into cumulative distribution function CDF. And the black curve is the CDF calculated by error interim analysis. And we can also use the same method, but calculated using the S2S prediction model data for every lead time. So, for example, the green and the orange lead lines curve in the lead time X and Y days, and the area difference can be interpreted as the forecast arrow of the monsoon depression index in the HiCast data. So this is the HiCast CDF during Northern Queensland SPRE, and forecast CDF during the 2018-19 SPRE. And then we can find that basically it can the model can capture the tendency of the monsoon depression index relatively well. However, with longer lead time, it has a larger arrows, and the arrow that varies with the lead time can be interpreted using these figures. And this is the HiCast performance. The x-axis is the forecasting time, and the y-axis is the CDF sum of the difference or sum of the arrows. So we can find that in the short range forecast, BOM model has the smallest CDF sum of the difference, but it grows in the median range. And the ECNWF has the smallest arrow, and at the extended range, CMA model has the largest arrow. If we take a short-term forecast of the forecast baseline, we can find that BOM can maintain the scale as the short-term forecast as up to 3 days, and the ECNWF can maintain the scale the short range up to 10 days, and the NCEP and the CMA model can maintain up to 6 or 7 days. So this is so. Next, we are going to examine the SPRE in 2018-19 model performance, and we can find that during the entire 16-day forecast, we can find that CMA has the best performance among the 4 models, especially in the extended range. So on average, the model prediction performance for 2019 SPRE case was worse than expectation, except CMA model. And the results of the 4 S2S prediction models of this study suggest that monsoon depression can maintain the same level scale as the short range forecast up to 8 to 10 days. And the SM model has this has the largest arrows in the extended range. So we have examined the prediction scale of the monsoon depression index, and then next we are going to examine the rainfall amount in the SPREs. So the 15-day cumulative rainfall amount is CMORPH, and the S2S model HiCast can be in the DJF 3 months can be sorted to the percentile ranks or the PRs, and the black and the white box shows the PRs relative to the CDF, relative to DJF 3 months, 15-day cumulative rainfall. Sorry, white box is the PR during the SPREs and relative to the reference baseline, and the blue box shows the HiCast performance of the percentile ranks in the past HiCast SPRE, and the red red boxes shows the forecast performance of the 2018-19 SPRE event. So we can find that so the prediction skill can be measured by the root-mean square sum of the differences between the forecast and the observed percentile ranks, and we term it as the PRRMSE. So the box shows the high-cast multi-year spread of the PRRMSE, and the curve shows the 2018-19 forecast of the PRRMSE for this event. So if we take the medians of as the reference baseline, and we can find that the BOM for the BOM model, the 2018-19 event, after 4-day lead time, the error is larger than the high cast medians, and CWF can maintain a skill up to 8 days, and SF can maintain a skill only up to 5 days. But CMA model can maintain a skill in the entire 15 days, and this result is similar to what we have found in the monsoon depression prediction skill. Yeah, that CMA has the best performance in the entire 15 day. So the next question is that what are the possible causes for the poor prediction skill in the 2018-19 SPRE and accept the CMA model? So we try to consider the possible influences of the ER wave and the MJO, and then we choose two cases. One is 1999. The SPRE is only influenced by equatorial Rossby wave without MJO, and the 2007 is the SPRE influenced by only MJO without equatorial Rossby wave. And this figure shows the PRRMSE between these 2 years. So we can find that in general, the model can forecast the a larger root-mean square error in the 1999 that it's only influenced by equatorial Rossby wave, which is larger than that is influenced only by MJO. So we suspect that also MJO is helpful for extending range rainfall category forecast, and the equatorial Rossby wave influence can overwhelm the predictability associated with MJO if the model fails to capture the equatorial Rossby waves. So here comes to my conclusion and summary. And in this study, we have identified the 20-year record-breaking SPRE in 2019 with some floods, and it is modulated by mentioned oscillation and equatorial Rossby wave. And for the model prediction skill, we find that in the 2019 SPRE event, the model forecast was in general worse than expectation derived from the high-cast analysis, and which may be related to the prediction skill of the equatorial Rossby wave that enhanced the monsoon depression circulation. And the analysis procedure in this study can be applied to other regions. For example, we are conducting two additional SPREs. 2017-18, the Philippine SPRE associated with 3 successive tropical cyclones, and the 2020 anomalous strong Meiji front from and Yuan Huai river flood. So this is our study, and thanks for your listening.